Case Study in Economics by Stuart Nielsen. The Federal Reserve Bank's Open Market Committee holds its meetings roughly every 6 weeks, 8 times per year. At the conclusion of each of these meetings, they issue a statement. We have an example here, the most recent one from May the 1st. So this is the statement issued by the Federal Reserve Open Market Committee. If you looked at the previous one, it would be very similar. There would only be a couple of differences. If you looked at one from several years ago, there would be more differences. There would be paragraphs added and deleted depending on circumstances and depending on what they decided to put in the statement. In terms of the content of the statement and what it has in it, it will have a specific declaration of a short-term interest rate, the federal funds rate. In terms of information that tells you something about longer-term Federal Reserve actions and the economy on a longer-term basis, you have a bunch of vague, bureaucratic, difficult to interpret stuff. But I will going to see what kind of signal I can extract from such statements. I have acquired all of these statements going back to 2006, which turns out to be 106 of them. For my response variable, what I am going to use is the movement in the 10-year Treasury interest rate, so a longer-term interest rate. There are some other candidates that also have been used by other researchers. You can take a more medium-term point of view and use a 2-year interest rate. You can use exchange rate or exchange rate futures. You can use the movement of the stock market. Another thing that gets done is looking at market response on an intraday basis, given that the statements are released consistently at 2 o'clock in the afternoon. You can catch timing there. I don't have access to such data, so I'm using a 1-day movement of the 10-year Treasury interest rate. This is a description of the data preparation that I performed. So I take the statement, I make it all uppercase so that case will be ignored. I turn it into tokens using NLTK. I build a dictionary which will map from words to numbers. I standardize the length of each statement. I make them all 1,000 words long. The longest one in the sample was just slightly less than 1,000 words. So then I have an array of 106 rows and 1,000 columns to feed into my models. Before we step into some deep learning models, there are some non-deep learning approaches to getting a quantified signal out of these documents. So one is just to look at how long the statement is. So one idea might be if the statement is long, it's bad news. Now, I don't actually observe such a pattern here, but maybe if you took differences and compared a statement to the previous one, there would be something more interesting there. So that's one thing. Another one is the sentiment analysis that you do on a word-by-word basis. So there are dictionaries that you could use which will categorize words in various ways. So the categories I'm going to use here are just simple positive and negative. There are others, and these dictionaries, they are available on a domain-specific basis. So I'm using a financial version of the sentiment codings here, which I acquired from the website whatthefedsaid.com, WTFS, as it otherwise is known. So let's take a look at what I got out of that. So I find that a statement with a highly positive sentiment score with more positive words than negative words Doesn't necessarily have a different average rate change, but it has less volatility. We see a funneling in this data. The next slide just is the same thing, but it's normalized by the length of this document, so it's sentiment on a per word basis. Similarly, it shows a funnel shape. Now we go into some actual deep learning models. So model number one is going to be a binary classifier. So it's going to be a prediction on whether the interest rate just goes up or down. I have my 106 statements. I will split them 80-20, which gives me 84 training statements and 22 to hold out as test data. The structure of model number one is it will have a embedding layer. It has a bidirectional, simple recurrent neural network, and then followed by a time-distributed dense layer, and then flattened, and then go to a single dense sigmoid for the final prediction. The results when I train this model are disappointing. It turns out that with this small sample, we just have extreme overfit going on. The model, without much bother, starts churning out more or less perfect predictions on the training data, and it doesn't have any kind of useful prediction on the test data. So there's a disappointment there from model number one. So that's the assessment of the model number one. Overfitting due to a small sample. One more model that I try, model number two, is a similar model structure, but instead of a binary prediction, it's continuous prediction. So directly predicting an interest rate change. Also, for good measure, it did seem to make the results look better. There is a second bidirectional simple RNN layer in this model. Results of training model two. In 300 epochs, we have this beautiful graph. Training loss and validation loss both going down together. So that looks rather promising. So let's see what else we have here, right? So the overfitting, which we dramatically had in model number one, we apparently don't have it here. We still have an equally small sample, yet we have a promising looking result. However, when we go and take a look at the predicted versus actual interest rate change on the test data, if we showed this graph for the training data, it would look beautiful. It would all be sitting along a straight upward sloping line. On the test data, despite the fact that the loss statistics from the training look promising, it doesn't actually show a prediction which shows much success of actually extracting a valuable prediction, a valuable signal in these texts which have been fed. So this result on a training era, so the training process was learning something. Apparently it was merely learning the overall distribution and not anything specific to the texts associated with each event. So that's that's the overall assessment of the Model 2 results. Now, going back to the funnel shape, which we encountered a few slides ago here on the sentiment analysis, could we possibly have a similar thing in terms of the text-based prediction? Perhaps. Other runs that I did of this model fit that pattern a little bit better than this result here. So maybe there's something there. And So overall reflections on this modeling process. I have a small sample. Small sample plus neural network equals danger of overfitting. I certainly encountered that. It would have been potentially possible to expand the corpus here by using Federal Reserve publications of other types. However, that's getting into things that are a little bit less standardized, but that is something that other researchers in this domain have done. I could have come up with a transformation of the response variable, something to reflect that kind of funneling effect, getting a volatility signal rather than just a directional signal. And then, of course, there's also the other alternative versions other than a 10-year Treasury interest rate. Another thing that gets done by other researchers in the field is to control for confounders, because there would also be other news that happened on the same day that affected that interest rate response. Speaking of the related literature, these are two key articles which I used in preparing this analysis. And then we have the last slide containing YouTube URLs. Unfortunately, the YouTube URL of this video is not there because I'm still making it. Hopefully you won't lose any sleep over that issue.